Hello again. This is Math 1120 coming to you from the College at a Page, and the title of this lecture is Amplification, Attenuation, and Boundary Behavior, Part 1. As always, please be an attentive learner as you watch this video. By way of introduction, the decibel, abbreviated dB, was introduced previously, and it's used to measure the amplification, increase in strength, and the attenuation, known as a decrease in strength, of physical signals, including sound. We did some calculations with this last time, and this builds upon that physical foundation to consider the attenuation strength and begin talking about boundary conditions in a specific ultrasound context. And this could be, I suppose, subtitled Interaction of Sound in Media. Sound exhibits specific behavior as it travels in different media, including soft tissue. As sound waves propagate in the body, they move from one medium into another. For example, a pulse of sound may travel from heart muscle into the blood that fills the heart chambers. Fortunately, weak reflections are often created as a sound strikes a boundary between two different media. These reflections are the basis for the images that are created as we scan. So the remainder of the sound wave, however, not reflected, continues to penetrate deeper into the body until the next boundary is encountered. Then, at that point, another weak reflection is created, and so on, and so on, and so on. Unfortunately, sound continues to weaken as it propagates. The ultrasound transducer and system must be sensitive enough to receive and process these weak reflections into an image. As sound waves propagate, they also may change direction. We will talk about that as well. Comparing signals. Sound waves weaken or attenuate as they travel in a body. After a transducer receives a sound wave during reception, the sound wave is converted into an electrical signal. The signal is sent to the ultrasound system, where it is strengthened or amplified. In diagnostic ultrasound, we are often interested in the degree of attenuation or the extent of the amplification. A standard measurement tool called Decibel Notation is often used to report such changes as this. Decibels are based on a mathematical construct called logarithms. And here it says we will first discuss logarithms and decibels. As I've already in a previous lecture discussed logarithms, I'm not going to discuss it here again. And we have talked about decibels before again, but this is a good review. So decibel, which is abbreviated dB, deci stands for base 10, and Bell is named after Alexander Graham Bell. In diagnostic ultrasound, it is important to quantify the strength of sound beams as they are created and travel through the body. In addition, electrical signal strength and the brightness of images need to be quantified. The decibel is a common unit used for measuring these signals. Decibel notation is logarithmic, and I gave you the formula last time. I do expect you to know the formula and use the formula. Decibel notation does not measure absolute numbers, but rather decibels report relative changes. For example, relative changes include the signal strength doubles, or the signal strength is now 1/10 of what it used to be. So decibel notation is a relative measurement, it's a comparison, it's a ratio, and it is logarithmic. Decibels require two intensities. The two intensities are the reference or starting level intensity, that was the threshold of sound that we talked about last time, and the actual level at which, at the time of measurement. Decibels are a ratio. The measured level is divided by the starting level. Positive decibels. Positive decibels report signals that are increasing in strength or getting larger. It is important to know the mathematical meaning of the relative changes. When a wave's intensity doubles, the relative change is plus 3 decibels. When intensity increases tenfold, the relative change is plus 10 dB. Decibels can also be negative. Negative decibels describe signals that are decreasing in strength, are getting smaller. It is important to know the mathematical meaning of the two relative changes. When the intensity is reduced to half its original value, the relative change is minus 3 dB. When the intensity is reduced to 1/10 of its original value, the relative change is minus 10 dB. And when we're taking absolute values then, actually I guess these aren't absolute values, but this summarizes what we've talked about before in terms of decibel and what does it mean. So here's some examples then. A sound beam has increased from its initial intensity by a factor of 100. How is that described in decibel notation? Well, we know that 100 is 10 times 10, and 10 times in decibel notation is plus 10 dB. Therefore, the decibel notation used for this is plus 10 dB, and another plus 10 dB is equal to plus 20 dB. The reason you're adding these is because of the logarithm, as we talked about. Here is another example. A sound beam has increased to 1/100th of its initial intensity. How is this described in decibel notation? Since we know that 1 over 100 is 1 over 10 times 1 over 10, and 1 over 10 in decibel notation is minus 10 dB. Therefore, the decibel notation used for 1 over 100 is minus 10 dB, and another minus 10 dB again, because logarithms are like exponents. You add these, this is minus 20 dB. What is the meaning of a 6 dB change? 3 dB means 2 times bigger, so 6 dB is 3 dB, and 3 dB, so that is 2 times 2, or 4 times bigger. What is the meaning of 20 dB? 10 dB means 10 times bigger. 20 dB is 10 dB plus another 10 dB. Therefore, 20 dB means 10 times 10, or 100 times bigger. Here are some review questions that are actually taken from certification exams, and so we'll go over those. Every 3 dB change means that the intensity will double. Every 10 dB change means the intensity will increase 10 times. A reduction in the intensity of sound beam to 1/2 its original value is minus 3 dB. A reduction of the intensity of a sound beam to 1/4 of its original value is minus 6 dB. This came up in a problem that was in a previous video, and I worked through it in a VCM session. Minus 10 dB means the intensity level is reduced to 1/10 its original value. dB is a mathematical representation with and we have a multiple choice question here, and the answer is it is a logarithmic and relative scale. True or false? We need 1 intensity to calculate decibels. The answer is false. We need 2. We need the reference intensity, which is usually taken to be the threshold of hearing when you're studying sound matters. A wave's intensity is 2 milliwatts per square centimeter. There's a change of plus 9 dB. What is the final intensity? This is a multiple choice question. I wouldn't ask you a multiple choice question. I'd ask you to just come up with the answer. But the answer is C. It is going to be 16 megawatts per square centimeter. Make sure you understand these problems. If the final intensity of a sound beam is more than the initial intensity, then the gain in dB is, and you're supposed to pick plus or minus. That's plus because it was increased. If the initial intensity of a sound beam is less than the final intensity, the gain in dB, here the gain in dB was increasing. Here the gain in dB is positive because it also is increasing. If the initial intensity is less, it is increasing. If the final, oh yeah, this is just mixing up final and initial things. It's really the same question. Okay, now we're going to talk a little bit more about attenuation, which is reducing things. So sound waves weaken as they propagate in a medium. This decrease in intensity, power, and amplitude as the sound travels is called attenuation. Attenuation is determined by two factors, path length and the frequency of the sound. And here's an example. You can see a transducer. It starts out with a powerful signal, but it gets weaker and weaker as it goes through the medium. So first, the distance that the sound travels directly affects attenuation. The further the sound travels, the greater the attenuation and the weaker the beam. Distance and attenuation are directly related. They are directly related, but well, we'll talk about equations perhaps later. Second, attenuation of soft tissue depends on the wave's frequency. Attenuation is greater in higher frequencies than in lower frequencies. So frequency and attenuation are also directly related. Attenuation is measured in decibels and is reported as a relative change, not as an absolute change. For example, when a wave propagates and its intensity is reduced to 1/10 its original level, we say the wave has been attenuated 10 dB. Now we could have said minus 10 dB, but we already said attenuated, so that word is there already, so that's why it is. So here's a little summary of some of that. More attenuation is associated with longer distances and higher frequencies. Less attenuation is associated with shorter distances and lower frequencies. And here you can see the amplitude, or expressing the sound signal as a like a pressure wave, but you can see that the strength of the signal is being attenuated, and so this is another representation of the same kind of picture. Note, when the reporting attenuation is dB, authors will often omit the negative sign. I guess I already talked about that over here. They might just say 10B of attenuation, and then that means minus 10 dB. Now, there are three processes that contribute to attenuation. There can be reflection out of boundary when you go from one medium to another. There can be scattering of the signal, and the signal energy can also be absorbed. Okay. A sound wave strikes a boundary, and part of it is reflected, and part of it is transmitted and also refracted. We will talk more about that, but that is one form that we have. And there are two forms of this reflection. One of them is called specular, and the other one is called diffuse. Specular bounces off cleanly, and we'll talk more about this, but the incident angle is going to be equal to the reflected angle measured relative to the normal. We'll revisit that again, but that is specular reflection, and that occurs when a wave strikes like it's striking a mirror. And one limitation is that this causes, the wave is basically bounced with specular reflection. We say the scattering is diffuse. Whenever you have an irregular boundary, the signal comes in, it's bounced all kinds of different ways off this. That is called diffuse reflection. Also, scattering can happen, especially when you're striking a very small object, and so and that's especially an example when you're doing studies about lung tissue. Higher frequency sound beams scatter much more than lower frequency beams. Scattering is directly related to frequency. The higher the frequency, the more the scattering. One particular form of scattering is called Raleigh scattering. When the dimensions are much smaller than the wavelength that you're using. And Raleigh scattering is proportional to the fourth power of the frequency. And so when you have these scatterings, it is less organized or more organized, and that is summarized in this table. So let's summarize what we've learned about reflection and scattering then. So the higher the, in fact, I think this actually is a nice summary up here, and I have more words here that you can read if you choose to. It just summarizes what we've talked about. It also is possible, however, for the medium to absorb some things. The third and most sizable component of attenuation is absorption. Absorption occurs when ultrasound energy is converted into another energy form, such as heat. And we will discuss, I think we've actually talked about it before. Some people are concerned about the heat in ultrasound. The higher the power, the bigger this is a concern. Like scattering, absorption is directly related to the frequency. As a result of absorption, higher frequency waves attenuate more than lower frequency waves. Sound traveling in bone undergoes extensive absorption. We will continue this discussion in the following lectures, so stay tuned. For now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're in this all together. May God bless you all.